So looking at number 9, we're asked to determine if the vector field is conservative. So the first component here is the P component, the second one is the Q component. We should be looking to see that the first order partial for P with respect to Y is equal to the first order partial of Q with respect to X. Alright, so it's essentially the X component, quote unquote X component, comma Y component. So we're taking the first order partial of one with respect to the variable associated with the other. Alright, so P 4x e to the sine y. So partial P with respect to y would be 4x e to the sine y times cosine of y. Then Q, now that's kind of a mess, but we can clean it up a little bit, because 1 over secant of y is the same as saying cosine of y. So we have 2x squared e to the sine y cosine of y. So the first order partial with respect to, or of Q with respect to X is just going to be 4x with that, all that other stuff, e to the sine y times cosine of y. And so we have it. So number 10, they're asking us to find a potential function for the vector field. First thing we have to do is make sure that it's a conservative vector field. So we have our P and Q. Now, very important, whatever we establish as the vector field, if it's going to be something that we can find a potential function for, as in the components or make up a conservative vector field, then it needs to be the gradient vector of some function f. Alright, so that's an assumption that we make going in. The best we can do is verify that it's a conservative vector field. So the first component here can be thought of as the first order partial, I don't know why that came up, of f with respect to x, which is really the P component, and that's 8 minus 3x squared over y plus 5x to the 4th y squared, poor quality 4. The first order partial of f with respect to y, which is known as q, is the other component of 6 plus x to the 3rd over y squared, blah blah blah. Alright, so what we're going to do is find the first order partial of P with respect to y. Alright, so that's in effect the second order mixed partial of the original function f. Alright, this is happening with respect to y. So I'm going to rewrite before we get into that. So 8 minus 3x squared y to the negative first. Let me just kind of move some things over here. Plus 5x to the 4th y squared. So 8 goes away. We're looking at 3x squared y to the negative second plus 10x to the 4th y. Alright, so if I find my first order partial for q with respect to x, again, a quick rewrite, 6 plus x to the 3rd y squared plus all that remaining good stuff So plus 2x to the 5th y. We're differentiating this with respect to x. We're looking at 3x squared, y squared, plus 10x to the 4th y. Alright. Oh, sorry. There should have been a negative second. There should have been a negative second. And now, and really the only reason I picked up on that mistake was because we knew that if it was going to be conservative, then the first order partials of P and Q would have needed to be equivalent to one another, and they are. Alright, so therefore F is a conservative vector field. Oh, conservative vector that would lead to a vector field. Right, but we say conservative vector field. Right, so now we go through the process of verifying or determining a potential. So now what we can do is kind of latch on to these relations or relationships, which we haven't really used yet, but we can use them now, and that is partial f with respect to x is equal to p, which leads us to partial f is equal to p dx, or delta x. You integrate both sides, we should get back to the function f, but we would integrate with respect to just the variable x, its partial integration, the function p. Alright, so this whole thing, p, I'll take this variation of it. We would be looking to integrate with respect to x. Alright, so reverse of the power rule for each part. We're looking at 8x minus x cubed y to the negative first plus x to the 5th y to the second, but then it would be some function that we'd call c of y. Alright, so some function c of y that we don't know, but we know it's not just simply a constant, it's a constant function. Alright, so we could do the same thing with that other relation that we have, and that is partial f with respect to y is equal to q, which gives us the other differential equation. Well, it is a differential equation, but in differential form. Which we can integrate. Oops. So we can grab this one, integrate with respect to y. Oop. Kind of melted in on that integration symbol. Alright, I'm just going to resize here. So f is going to be equal to, well, too thin, let's go 35. 6y minus x to the third y to the negative first, and then plus x to the 5th y squared plus c of x. Alright, so we have those two differential equation solutions, but they're in general form. We want a particular solution. Alright, so and get a little bit more work to do. So what we could do now is look at each one of these solutions and compare it to really what we started with, because we know partial y, partial f with respect to y was equal to 6 plus x to the third or y squared and all that good stuff. But what we have here is a new expression that we could use to represent the function f. Right? So what we can do is find the first order partial of this with respect to y. So that would zero this out. It would give us x to the third, y to the negative second, plus 2x to the fifth y, plus c prime of y. Alright, and then by setting that equal to this definition, we can arrive at an expression representative of c prime of y. And then it would just be a step away from figuring out what c of y is, and then we'd have a solution for this differential equation. Alright, so they're both equal to the same thing, essentially. Alright, so they have to be equivalent in some capacity. Alright, so if they're equal, and let me just kind of resize it again, because why not? And you can see that everything in terms of the fill in the blanks is in terms of c of y. So that seems to be the focus of this. All right, so we can go after it either way, but this seems to be the avenue that the problem is suggesting that we go down. All right, so we'd be looking at x to the third, y to the negative second, plus 2x to the fifth y, plus c prime of y is equal to 6 plus x to the third, y to the negative second, plus 2x to the fifth times y. All right, and we'd see cancellations abound here. This goes with this, and this one with that, and it looks like c prime of y is just equal to 6. And so if I want to figure out what the value, well, so I have that part. Let me just kind of tuck this away now, so I could just pop that right in there. Oop, 6. So then c of y would be the next item on the list. So I'd be looking to anti-differentiate this. So I could write this as dc dy is equal to 6, in which case I could write it as dc equals 6 dy. Integrate c is equal to 6y, that's not a 6, 6y plus c. Alright, now that c is really the one on the left, so to make this as confusing as possible, that's really c of y. So let me actually just make that the notation. So that c of y is the constant function, but we're able to replace that with a function that includes a constant. All right, so let me just clean this up. We're resizing again. Lots of resizing. And so our solution here would be f is equal to all of this, but instead of the c of y, it would be plus 6y plus c. And that would be what we would call f, or f of xy. Alright, so in terms of getting our ducks in a row here, 6y plus c, and then that whole shibiggity bangity boomity bombity boobity 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 boom would be all this. Although, I just caught a little typo here. It shouldn't be lowercase f, just based off the notation that was used for this question. It should be capital F.